Hello! For our project, we decided to model the speed control of a driverless car. On average, there are 6 million car accidents in the United States per year. On a national level, nearly 1.4 million people are killed in or by vehicles per year. Generally speaking, these accidents and subsequent deaths are a result of human negligence and inability to respond to challenging situations quickly and accurately. Self-driving cars will help mitigate the risk that vehicles pose by removing human error. They also help by reducing the labor required for shipping and other important services. Control engineering is required for the operation of self-driving cars because they demand a lot of feedback from their environment and their own parameters to be accurately controlled. Because quick changes in speed or required speed are common while driving, adequate disturbance rejection is also needed for self-driving cars. In the case of a car accelerating down a road, air resistance will interfere with the current speed. In order to maintain the speed limit while the car accelerates, feedback will be needed to maintain equilibrium. Our goal is to improve transient response time of the cruise control in a car by comparing the car's increasing speed with the equilibrium speed. These specifications will be discussed with greater specificity during controller design. The force that the engine applies to the wheels is measured in newtons, and the resulting speed of the car is measured in meters per second. The parameters of the system involve the mass of a car in kilograms and a disturbance force acting against the car in newton seconds per meter. The generic transfer function for the system can be found on the slides. A mass of 1,050 kilograms was used to represent the weight of the car, while a damping force of 210 newton seconds per meter was used to represent air resistance. An input of a 2,000 Newton step response was applied to the model to represent a car accelerating from rest. The step response given from Simulink, given open loop parameters, is pictured in Figure 1. We will now move forward to talk about the analysis of our model.
In this part, we will talk about the transfer function of open loop system. So, this is a first order system with only one pole located at the left half plane. Given the pole location, it can be said that the loop system is Beeble-stable. A simulation of root locus verifies the stability of the system, which can be found in this slide. Also, the open loop system is a type 0 system, which will give a finite value with a step input for the steady state error. Given a pole value of 0.4118, the settling time will equal to 11.17 seconds. The rising time equal to 5.34 seconds. The graph in this slide using 2% settling time, which will lower than 11.17 seconds.
In the design section, we will address the specifications the system must meet, as well as how to meet them. These target specifications are as follows: a closed-loop settling time of 7 seconds, 0 steady-state error to a step response, and finally, the system must include disturbance rejection. The closed-loop settling time should be 7 seconds because that is the target acceleration time for the vehicle. Additionally, the vehicle must have 0 steady-state error. If the target velocity was 0 and steady-state error was present, the vehicle could be moving when it should be at rest. And finally, the disturbance rejection will be necessary for the vehicle to travel uphill and maintain its speed. The figure shown is a graph of the possible pole locations to achieve a settling time of 7 seconds. In order to achieve 0 steady-state error, we must convert this system to a first-order system using an integral controller. In this closed-loop diagram, the bounds for stability are Ki should be positive and Kp should be greater than negative 432.381. The higher the value of Ki and Kp, the better the closed-loop system response. D of S represents the input for the disturbance. Finally, the root locus for the closed-loop system that contains poles that meet our specifications is shown below. In the next section, Scott will simulate our controller design to verify that it meets these specifications.
We will now discuss the closed-loop response of our system. First, we will look at its step response and make sure that it meets our specifications. Our initial specifications were that there was 0 steady-state error to a step, a settling time of less than 7 seconds, and adequate disturbance rejection. In the graph, you can see that our rise time is 1.5 seconds and our settling time is 5.3 seconds. This meets our specifications. Now we will discuss the disturbance rejection of our system. In the graph, you can see the system's response to a step disturbance input. The output is very small at its peak. This is because our feedback system has the controller in the feedback loop for a disturbance, and the gain on our controller is very high, meaning that its effect on the output will be very small. Disturbances that our system could see would be things like gravity, wind, or potholes. These things would act as step disturbances because they would be static as they are happening. Here is the root locus for our system. Our system's controller has a proportional gain of 947.591 and a differential gain of 568.555. We also added a gain on top of that of 1.26 to move the poles farther out and increase our system's effectiveness. When factoring this in, you can see that our system has our system's controller will be 1193.965 divided by S times the quantity of S plus 0.6. This adds a pole at 0 for our system and a 0 at negative 0.6. You can see these both in the root locus. The pole at 0 causes our system to have a 0 error to a step response, which was in our specifications. We will now talk about the robustness of our system, because our system seems to be very adequate, because at no gain will any of the poles enter the right half plane. As you can see, the phase margin only gets better for our system as you increase the gain. This is because of the 0 that is added by our controller, which pulls up the response or the phase response at higher frequencies. So as you increase the gain, the phase response or the crossover frequency will increase, and your phase margin will increase as well. There is no gain margin for our system, which we also saw on the root locus. This is because the phase margin never passes 180. The gain is only limited by the actuators we can get, and in general, our gain, increasing it, will improve the response of our system in every way. Next, we will look at how time delays affect our system. Below is a graph of a 1.1 second time delay added to our system with a step input. You can see that the peaks decrease and our system remains stable. Now there's a graph of a 1.2 second time delay in our system. You can see that the peaks are increasing and the system has become unstable. This is because the maximum time delay our system can tolerate is 1.1985 seconds. This is reasonable because our system will be implemented inside the car that it is controlling, and so we should not expect very much delay. Next, we will look at the references.